Welcome to lecture 13, phase diagram part 5, engineering metallurgy. In the last class, we have studied phase diagram type 4, and today we are going to study on rest of the phase diagrams and rest of the reactions that take place during the solidification of metal. The type 5 is about peritectic reaction. It is basically the reaction that occurs between a liquid and a solid. Upon cooling, a liquid and a solid reacts and converts into a different type of solid. That is, and that occurs isothermally. There is no temperature change, but liquid and solid reacts to produce a new solid. That's called new solid 2. And new solid usually is an intermediate phase. That means in the type 4, we have studied what is meant by intermediate phase. It is a compound, and most of the cases, the liquid and solid produces a intermediate phase. That's the new solid is actually an intermediate phase or compound alloy. And sometimes it can also be the terminal solid solutions too. This is one of the schematic diagram. In the ideal case, the schematic diagram shows the peritectic reaction, and any reaction in the phase diagram is represented by a horizontal line. So in the case of eutectic reaction, we know that it is indicated by E. The eutectic reaction line is a horizontal line. Similarly, the Tp is the peritectic temperature, and the line Tp and D is called the peritectic reaction line. And this is horizontal line because the peritectic reaction basically takes place at a constant temperature, and the peritectic reaction is about a liquid and a solid reacts to form a compound or a different type of solid. And if we look at the example of an alloy to understand it more clearly, let's move to this one. In here, if you consider alloy 1, how alloy 1 solidifies when the temperature is dropped, then we will be able to understand how the peritectic reaction works. To give a expanded view of the diagram, or to understand it more clearly, if you look at the alloy 1 at high temperature above the liquidus line, the alloy 1 is completely soluble in the liquid state, and it contains like 10% B. Because this alloy is 10% B of concentration, the liquid solution will have the uniform distribution of A and B, and B will be soluble in A. When the temperature drops below this liquidus line, then solidification starts. If we draw a tie line in that region, if we draw a tie line in here, then at this temperature, there will be solid of pure A, and there will be some liquid present. When the temperature is dropped from this temperature below, then the more and more solid will be created, which is indicated by this length. This length actually indicates the amount of solid. That means solid A is increasing when the temperature is decreasing. Okay. Just before the peritectic temperature line, when this point is reached, at this point there will be solid of 100% A, which is called primary A, and the liquid solution will have like 40 B. The chemical composition of the liquid solution will be 40 B, which is indicated by this point. This point, because we know that tie line is this whole length of the line is the tie line, and this tie line on the left side, this indicates the chemical composition of solid, which is primary A, which is 100% A, and this point indicates the chemical composition of liquid, and the liquid has 40 B, or 40% B. And if we calculate the relative amount of solid and liquid present at this temperature, then it is like liquid solution have 25%, and the solid will have like 75% solid will be produced. So when the temperature reaches Tp, that means the peritectic temperature, at that temperature will remain constant, and the peritectic reaction will take place. And the peritectic reaction says that there has to be a liquid and a solid which will react and form a different type of solid. Okay. So when the reaction takes place, then some of the A, from the 75% A, some of the A will be used to with the 25% liquid to form a different solid, which is indicated by this vertical line, and this vertical line actually indicates a AMBN. That means this is a intermediate alloy phase. That means that this is a compound. That means the solid that has been produced, solid A that has been produced from this point to this point, some of the A will react with liquid to form a different solid, which is AMBN. Okay, and if we look at the reaction here, like the liquid has like 60A 40B, so this is the same 60A, either 60A or 40B, whichever you say, it will be the same, and the 100% A. So there will be like the 100 solid, some of the solid A and the liquid, 25% liquid and 8% solid. Solid A will react to form 33% AMBN. Just below the peritectic temperature line, when we consider the chemical composition or relative amount of phases, then we will see that there is 33% AMBN produced after the reaction, which contains 30B. That means 70A, 30B. The chemical composition of the compound is 70A, 30B. And the primary A has been reduced. That means 67% primary A is produced. That means before the peritectic reaction, there was 75% primary A, but after the peritectic reaction, we have found that the primary A has been reduced to 67%. That means 8% of primary A contributed to the reaction with the liquid of 25% B to produce 33% solid AMBN. So that's how the peritectic reaction works. And when the temperature is dropped below this temperature, then it will remain the same. The relative amount will also remain same. That means 67% primary A, and with 33% AMBN will remain at room temperature. Okay, any question? Okay, let me repeat it once more, just for clarification. For alloy 1, the liquid will have the uniform chemical composition. When the temperature drops below this liquidous line, then solid A starts to produce, and just before the temperature Tp, the percentage of solid A is 75%, and the liquid solution will have 40% B, and the total amount of liquid will be 25%. And after the peritectic reaction, if we look at the chemical composition and relative amount of phases, then the chemical composition shows that we have AMBN of 30B, 70A 30B, which is 33%, and primary A is 67%. That means after the peritectic reaction, the 75% A has been reduced to 67%. That means there is 8% A, the 8% A is solid A reacted with the 25% liquid solution of 40B and then produced 33% AMBN, which is a compound. Okay, and that proportion, that means 33% and 67%, 33% AMBN and 100% A, 67% of 100 A will remain up to the room temperature. So do you have any question? All right. Okay. Next, let's move to what happens on the other side. If other side of the AMBN, the other side of the compound, To see that, we have to consider the alloy 2, which is on the other side of AMBN compound. To look at that more carefully, if we at a high temperature, that means the above the liquidus line, and the liquid solution will have, because this alloy is 35% B, so liquid solution will have uniform distribution of A and B, completely soluble. And when the temperature drops below the temperature T2, then solidification starts, and there will be primary A of 12.5%, and liquid solution will have 40B, which is 87.5%, just before the peritectic temperature line. And after the peritectic reaction, if we look at it carefully, after the peritectic reaction, the liquid solution will have like 50% liquid 50% 40B of 50%, and AMB and the compound is 50%. That means the total of primary A 100% that has been produced before peritectic reaction has been reacted with the liquid solution, some of the liquid solution, to produce 50% AMBN, and 50% liquid solution will remain in there. That means in this region there will be still some liquid and some solid, that is compound. So there will be no A, 100% solid A will be present in this region. This region will only consist of the liquid and AMBN. And when it comes, temperature is dropped more before the eutectic temperature line. This is the eutectic temperature line. At this eutectic temperature line, the chemical composition is like AMBN is 30B and liquid solution will have 80B. And when the liquid solution is 80B, that indicates the eutectic composition. When it reaches liquid solution is at eutectic composition, then liquid solution will be converted into eutectic mixture. And this eutectic mixture will be consist of AMBN and B. Because if you look at the previous slide, then we'll see that after the eutectic reaction, if we draw a tie line, it consists of pure metal B and AMBN. So the mixture, the eutectic mixture will be consist of AMBN and B. But the grains that has been produced, that means crystals that has been produced for AMBN, will remain the same. That means the AMBN will remain the same, and after the eutectic reaction, the liquid that is remaining in here, in this region, that liquid will be converted into eutectic mixture of AMBN and B, and that will remain at the room temperature. Okay, any question? So no question? All right, if you don't. So that's what I was talking about, like the liquid that have like 60A, 40B will react with the total solid 12.5% solid A to produce solid A and B and of 50%. And then 50% liquid will remain in this region at this temperature, just below the peritectic temperature line. Okay, so the next is the two liquids partly soluble in the liquid state. In this case, what a monotectic reaction actually takes place, and that is the type 6 phase diagram. If you look at the phase diagram, type 6 phase diagram, it will be similar to the other diagrams, but only difference is in the liquid state. And liquid state, these two lines, CD and FG, this two line actually indicates the solubility of liquid 1 and liquid 2. Liquid 1 will be with the temperature. If the temperature increases, solubility of B in liquid 1 increases. Okay, and in the case of liquid 2, the solubility of A increases in liquid 2 with this following this line. And in this region, in between these two lines, CD and FG, there is liquid 1 and liquid 2 will stay separately. Okay, that means they don't mix with each other. That means they are partly soluble, but not completely soluble in this region. But if the temperature is very high, then they might be soluble. They might produce a single liquid. Okay. And when the temperature drops from, let's say if you consider the alloy X, the temperature drops below this liquidus line CTA, then the solid A will produce and liquid 1 will be there. And at this temperature, at this line, TM is the monotectic reaction line. And at this temperature, when it reaches this temperature, then the solid A, if you look at the reaction, monotectic reaction, it is called the liquid. One of the liquid will produce a solid and a liquid and a different type of liquid. Okay. So in this case, when the temperature drops to temperature X2, monotectic reaction takes place. And after the monotectic reaction, the liquid 1 that has been present before the monotectic reaction will convert it into solid A and liquid 2. That means if we look at the microstructure at this point, then it will be the uniform microstructure of the liquid 1. And just before the monotectic reaction, if we look at the microstructure, then there will be some grains of metal solid A, and rest of them will be liquid. And that is the liquid 1. Once the monotectic reaction has been taken place, then the liquid 1 will be converted into liquid 2 plus solid A. That means just after the monotectic reaction, liquid 1 will be converted into solid A and liquid 2. That means if you look at the microstructure just after the monotectic reaction, then there will be grains will be larger. The grains of A will be larger. That is A. That means more A will be produced, and the liquid that is remaining in there will have the composition of liquid 2. And if we calculate the relative amount of phases, like just before the peritectic reaction, if we consider the how much solid is produced, like A will be 50%, A will be 50% A, and liquid 1 will be also 50%. But after the reaction, after the monotectic reaction, if we calculate the relative amount of each phases, then we'll see that the solid A, percentage of solid A can be calculated from this line, this length, and percentage of liquid will be calculated from the other. That means this line has like 60% B. That means 60 minus 10. That means the percentage of solid will be 50 divided by 60. This will be the percentage of solid, and percentage of liquid will be given by this length. This length will give us the percentage of liquid, which is 10 divided by 60. From here, we can get the percentage of liquid L2. And the chemical composition, the A will be 100% A, and for liquid 2, the chemical composition will be 60B. That means, and the chemical composition of the liquid 1 will be 20B. 20B. This point will give the chemical composition of liquid 1. So liquid 1 has the chemical composition of 20B. After the reaction, this liquid 1 has converted into solid A and liquid 2. Liquid 2 will have the chemical composition of 60B, and solid A is 100% A. Okay, that means more solid A will be produced, and the liquid 2 will have a composition of 60B. That is, the amount of B will be uh, more compared to the liquid 1. In the liquid 1, amount of B was only 20B, but in the case of liquid 2, the chemical composition, if you look at the chemical composition, then we see that in the liquid 2, the more B is concentrated on liquid 2. Then when this, the temperature drops more at X3, then eutectic reaction will take place. And because of this eutectic reaction, there will be the mixture of, since on the other side there is a solubility of A in B, which indicates by this JB line, and this line indicates the solubility of A in B. So the eutectic, the rest of the liquid that has been when the temperature drops from this point, then more and more A will be produced. And if you look at the microstructure just before X3, then we'll see that there will be grains, and this will be liquid 2. This is liquid 2, and also this is liquid 2, and these grains will be solid A. And this liquid 2 at this temperature will be converted. If we look at the microstructure after the after the eutectic reaction, then we'll see that the previous grains will remain in there, and the liquid 2 will be converted into the mixture of eutectic mixture of A and beta. A plus beta. Okay. Once the eutectic reaction has been taken place, and at the room temperature, this will remain the same. Okay. Any question?
No, sir.
All right. Now, if we look at the alloy Y, in the case of alloy Y, at very high temperature, there will be only single liquid. But when the temperature drops below this line, then liquid 1 and liquid 2 will be separated. How do we determine the how much? What is the chemical composition of liquid 1 and liquid 2? In that case, at this, if we want to determine the chemical composition of liquid 1 and liquid 2, then we have to draw the tie line between these two, because liquid 1 and liquid 2 is two different phases. Okay, and if we draw the tie line, then we will get the chemical composition of liquid 1 from here and chemical composition of liquid 2 from here. And if we want to find out the percentage of liquid 1, then we have to consider this length for liquid 1, and for liquid 2 chemical composition, we have to consider this length. Okay, so it is similar to the other things in the two-phase region. You draw a tie line and then you find out the chemical composition and the percentage amount of liquid 1 and liquid 2. And when the temperature drops, comes to Y2, drops at reaches Y2, then the liquid 1 will have a composition of 20B, which is a favorable condition for taking place the monotectic reaction. Then liquid 1 reacts to form solid A and more liquid 2. That means the percentage amount of liquid 2 will increase, and also solid A will be produced. And once the temperature comes to the eutectic temperature, then liquid 2 will be converted into the mixture of A and beta. So at room temperature, there will be solid A, grains of solid A, along with the grains of eutectic mixture. Eutectic mixture A and beta, and that will remain up to the room temperature. And on the other side, if you consider this one is similar to the type 2 diagram, type 2 or type 3 diagram. The alloys that you want to consider, it will be the same. Liquid 2 will be converted into solid A, and liquid 2 will remain at, and after that, after the eutectic reaction, there will be solid A and the eutectic mixture of A and beta. Okay, any question? All right, then we move to the next one. This is type 7. In this case, two metals insoluble in liquid and solid state. That means the metals are not soluble in any way. That means you raise the temperature, they don't mix with each other, and when solidified, they don't mix with each other. It is a very simple type of phase diagram. If you look at this, then at very high temperature, the the element A has a melting point temperature of TA and element B has a melting point temperature of TB. That means when you increase the temperature, then solid B will be completely molten in here. That means solid B will be converted into liquid B. And when the temperature reaches this temperature, solid A will converted into liquid A, and they will stay separately. They will not mix with each other. And upon cooling, when you start cooling, then at temperature TA, solid A starts to solidify, and the solid A at the same temperature, solid A completely solidifies, but liquid B does not have any change in the liquid B. But when the temperature drops below TB, then solid B also starts to solidify. Now the question is how the solid A and solid B will remain in a container. If you consider a container, then if solid A has higher density, then solid A will precipitate at the bottom, okay, and the liquid B will be on the top, and it will be reversed. If the density of solid A is less than liquid B, then solid A will precipitate on the top, okay. And once the temperature drops below TB, then solid B gets solidified on the top. Okay, so that's how they will remain separately. They will not react with each other. They will not mix with each other. It's very simple type of phase diagram. Now the allotropy, the transformation in the solid state. In the case of solid state transformation, allotropy is one of them. Allotropy is defined as the existence of different type of crystal structure depending on the temperature, and if it is reversible, then it is called the allotropy. That means if a metal can remain in different type of crystal structure, for example FCC or BCC structure, with the temperature the structure can be changed, and that can be indicated by a point in the vertical line of the pure metal. Okay, and iron, tin, manganese, cobalt, this material actually shows this kind of allotropy. That means if you raise the temperature, then the crystal structure has been changed, and if you drop the temperature, it returns to its initial position, initial structure. Usually they are called gamma loop. If you look at this figure here, in this case, the material when metal A is solidified at this temperature, it's completely solidified, and solid will have solid is alpha, which is a BCC structure, body centered cubic. And when the temperature reaches at this point, then the pure metal A actually converts into gamma. Okay, and then gamma will have a structure of face centered cubic. When the temperature drops below this temperature, and this temperature below this temperature, it again goes back to body centered cubic structure. So it is a temporary structure. Temporary structure of BCC is produced between these two temperature. Okay, and this is called the gamma loop. That means it is closed loop, and sometimes it can be also open loop. But before going to that, I would like to clarify one more thing. That is when there is an alloy in here, in that case, what will happen? The solid that is formed in here will have like BCC structure, 100% BCC structure in this region. And when it comes to this point, then some of the solid will start to convert into gamma. So from this temperature to this temperature, the transition from body centered cubic to face centered cubic structure occurs, and after this temperature it is completely gamma. That means completely face centered cubic structure, and below this temperature it again starts to disintegrate. That means gamma disintegrates into alpha, and after below this temperature, it is completely alpha again. And this thing that is called the allotropic change. That means crystal structure changes to a different one, and then it comes back again to the initial structure. And this is the closed loop. Sometimes it can also be the open loop like this. It is a equilibrium diagram of iron and nickel. In this case, this gamma loop is open. That means once the solidification is complete, if you look at the pure metal Fe iron, the pure metal iron, in this case, in this region, the delta structure is produced, and after below this 1400 degrees Celsius temperature, the structure is gamma, okay, which is face-centered cubic. The delta is also is body-centered cubic, and then it is converted into face-centered cubic. And then when the temperature drops below 910 degrees Celsius, then it comes back again to the body-centered cubic structure, which is called alpha iron. Okay, and it occurs for the whole region. For example, if you come here, then there will be gamma will be produced in this region, and after this line, there will be again alpha will be produced in this region. Okay, so this is the open gamma loop. So the next one is the order disorder transformation. In the case of order disorder transformation, in the formation of substitutional alloys, solid atoms do not occupy any specific position rather than distributed at random. That means in the disordered condition. That means when a substitutional type solid alloy is produced during solidification, the atomic position is not completely uniform. Okay, a disordered condition can be obtained, and in that case, at room temperature, before reaching to the room temperature, there is the arrangement of the atoms are changed, and that is called the order disorder transformation. Okay, in the case of order disorder transformation, if you look at this image, this is solid solution, and in this case, this A atom and beta atom. And A atom and beta atom is not uniformly distributed in here. Okay, and after a certain temperature, when temperature continues to drop, at some temperature, the distribution of these atoms, beta atom in A atoms in the matrix of A atom, they get ordered fashion. Okay, they distributed into ordered fashion by diffusion. Okay, and this is called the transformation, order disorder transformation. And this actually changes the chemical property too, because if there is more concentration of A and less concentration of A, that actually defines the mechanical characteristic of this material. So when it is in the ordered condition, then it will have a different property. Okay, and the ordered solid solution is sometimes called superlattice because it shows a very high quality material. It indicates a very high quality lattice or crystal structure. So in the case of phase diagram, if you want to see that order disorder transformation, then gold copper equilibrium diagram can be seen. In here, alpha is a solid solution that is formed after cooling, and when the temperature reaches this at this temperature, below this temperature, the alpha actually gets ordered. Okay, and this is called the alpha dash. Is called the ordered solid solution, and that this is called the superlattice. And the same happens in the case of alpha dash. Okay, this also have the similar ordered arrangement, but the arrangement will be slightly different from this one, because this one will have more gold atom than copper atom. So it will be alpha dash will be like in the matrix of gold, and alpha double dash is the in the matrix of gold. Copper will be distributed in the matrix of gold, and in the case of alpha dash, the gold will be distributed into the copper solution. Okay, so this is how the order disorder transformation takes place before reaching to the room temperature for the solid solution alloy. So the next one is the Eutectoid reaction, and this is a solid state reaction. It does not involve the liquid to be present in this in the phase diagram is similar to the eutectic reaction, but it does not involve liquid. A solid phase is transformed into two different solids. That means in the case of eutectic reaction, a liquid is converted into two different solids, and in the case of eutectoid reaction, a solid is converted into two different solids. Okay. So to look at that, in the case of eutectoid reaction, this line ONP indicates the eutectoid reaction line. Okay. So at this temperature, temperature line from O to P, the transformation will occur based on the eutectoid reaction. That means solid will convert it into liquid phase. Okay. So if we look at this diagram of alloy 1, in the case of alloy 1, when temperature reaches X1, then TA will start to produce, metal A will start to produce, and X2, metal A completely complete solidification has been complete, and then gamma will be produced. And when temperature reaches X3, then from gamma, that means gamma is the pure solid A, and from that gamma, some alpha will start to produce. Okay, and alpha, it will be the mixture of alpha and A. And when the temperature reaches X4, then the composition of A will become the composition of eutectoid composition. Okay, and when the composition of more and more alpha will be produced, when the temperature drops from X3 to X4, more and more alpha will be produced, and the A will be reduced, and the composition of A will be just before the eutectoid reaction point. The composition of A will reach the eutectoid composition, and at this eutectoid composition, A will convert into the eutectoid mixture of alpha and beta. Okay, that means solid A is converted into solid A is solid 1 is A, which is converted into solid alpha and solid beta, and this is called the eutectoid reaction. Okay, and on the other side, if you look at the other side, then still in here gamma will be present in this condition, and when the temperature reaches below this temperature, then beta will start to produce. That means in this region it will be the mixture of gamma and beta, and when the temperature drops at this point, then the gamma will have if you look at this is gamma. So the gamma will have a chemical composition of eutectoid chemical composition, and gamma will be converted into in that case gamma will be converted into alpha and beta, a mixture of alpha and beta, and the final structure will look like this. That means initial alpha will be present in there. If you look at this alloy, that means if you consider alloy 1, then the primary alpha will be produced in there, and after the eutectoid reaction, then there will be the eutectoid mixture of alpha and beta present in the microstructure. And on the other side, if you consider in this side, then in this case there will be the gamma beta will be present, pro-eutectoid beta will be present. In the case of alpha, there will be beta, and the mixture will be the alpha and beta mixture. Okay, any question? Okay, so the next is peritectoid reaction. It is similar to peritectic reaction, but it does not involve liquid. It occurs in the solid state. Okay, similar to the peritectic reaction, but does not involve liquid. And in this reaction, two solid phases transforms on cooling into a new solid phase. That means in this case, solid 1 and solid 2 reacts to form solid 3. That means after the eutectic reaction, if you consider an alloy in here, then after the eutectic reaction, alpha and beta will be present, and alpha and beta below this temperature, EF temperature, this line is called the peritectoid reaction line. In this reaction line, alpha and beta mixture will be converted into gamma. Okay, Or if you consider an alloy here, then there will be some alpha will remain, but some alpha and beta will react to form gamma, a different solid. That means two different solid produces a third solid. Okay. And if you consider this phase diagram, it is kind of same. If you consider an alloy in here, it is a pure A and beta, mixture of pure A and beta. And once the peritectoid reaction is completed, then A and beta will react to form gamma. Okay, and this line indicates the gamma line, and this is 100% gamma. Okay, any question? So the summary of the reactions in equilibrium diagram. The first we have seen the eutectic reaction, in which case the liquid is converted into two different solid. Okay, the liquid is converted into two different solid, alpha and beta, or A and B, whatever it is. And in the case of peritectic reaction, a solid and liquid reacts to form a different solid. That means a solid and liquid reacts to form a different solid. It can be symbolized like this. That means alpha and liquid will react to form beta. Okay. And monotectic reaction, it involves liquid. The liquid 1 will be converted into a different liquid and a solid. Okay. The liquid 1 will be converted into a different solid and a different liquid and a solid. Okay. And eutectoid reaction, a solid will be converted into two different solids. Yes. Okay. And in the case of peritectoid reaction, two different solid will produce a different third solid. Okay, this is the opposite reaction actually. In this case, all of the reactions actually we have shown here is upon cooling. Okay, so it will not be exactly the denation can be similar, but the condition is upon cooling. Okay, gamma will be converted into alpha and beta. In this case, alpha and beta will be converted into gamma. And alpha, beta, gamma actually indicates different solid phases. Okay. So that's all for phase diagram. This is a total phase diagram chapter is complete so far. So in the next lecture, we'll be talking about iron-iron carbide diagram. This is also a phase diagram, but this is the phase diagram between iron and carbon, a part of the phase diagram, because iron and carbon produces a compound which is called iron carbide, Fe3C. This is the iron carbide solution compound is formed, and we'll investigate this iron-iron carbide diagram more carefully, because most of the steels that are available with us, steel or cast irons, those are between these two, pure iron and iron carbide. Okay, so it is very important to understand it, and this iron carbide diagram gives a good insight for the heat treatment of steel. If you want to do the heat treatment, how to conduct the heat treatment, and at which temperature you should conduct the heat treatment, and what will be the final property of the material, that can be understood from this iron carbide diagram. So in the next class, we will discuss about iron carbide diagram.